So I'm back.
Yeah, I can. So now we're live. So I'm just gonna try to avoid that stop sending button.
Yeah, I see it. So maybe the new feature is to start it already in live mode.
Yeah. Okay, so Jim is here as well.
Yeah, you haven't cracked whip hard enough to break me free yet. Figure 1 or 2 more transitions, and that's all it'll take. I'm doing other stuff at the same time here.
So we're waiting for. Oh, now Espen is here as well. So I'm going to try to. So I have an option here on Espen's icon, present for everyone. I guess that means let him share his screen. Is that right, Patrick?
Yeah. So normal behavior is that Hangout is switching to the screen of the speaking person.
Mm-hmm.
And if you set it to share for everyone, it's fixed to one speaker.
Okay, so I guess now, Espen, if you start sharing your screen.
Right.
Hopefully we will see it.
I can try. Do you see it?
No.
All right. Google Hangouts is sharing a window.
I can see it.
Well, as long as you can see it.
I have a black window.
Maybe there's a delay.
That's a very long delay.
Yeah. Oh, now I can see it as well. Yeah. Good. We're ready.
Right.
So we have everything set up. Live stream is already running.
Yeah.
Everybody is logged in. Have you missed something, or can we start?
So
you know for sure that the recording is on?
Yeah, it says live and it has a button saying stop sending. So
that's great.
That's all I need.
Right. So should I just start?
Yeah.
Yeah.
Everybody there?
Oh, yeah. The list is complete.
Yep. Good. Okay. So it's UVVM, right? So before I start, I just want to show this slide because you also in these slides where they're showing that verification is now 50% of the total development time. But I think this is equally interesting because it says that debugging is a huge majority, or 43% of the total verification time. So that means debugging actually is probably the most important thing when it comes to verification. I think that's quite interesting. Right. So basically what we are aiming at when we do FPGA designs is quality and efficiency, of course. And we try to look at what are actually the enablers for that, because people tend to talk about languages and so on, but that's not the most important. What is most important is overview and readability. It's modifiability, maintainability. It's debuggability, as I just mentioned, and reusability. So what gives us all this in a good way? Still not a language. It's basically structure and architecture. It's basically the way we implement things. Exactly the same as when we do a design, really. It's the architecture that decides how efficient we are and the quality we get. And the same for verification. So UVM is trying to target these challenges. It's free and it's open source code, downloadable from GitHub. And there are 2 levels of functionality. By the way, do you all see the animation now? Is it working okay? Is it slow, or do you see it?
It's okay at my side.
Yeah, good.
Yes, okay as well. Yeah.
Good. So basically 2 levels of functionality. One is so-called as a base level utility library, and the other is the VHDL verification component framework, which uses utility library as a base. So I will not spend a lot of time on the utility library because it's quite simple, and you've seen a lot of the same features in other systems, but I'll just go briefly through some of the features. So it's basically a VHDL test bench infrastructure, has logging and verbosity control, alert handling, including also optional positive acknowledge on checks, some extended string handling, simplified randomization. Then it has, built on top of that, it has a few support, or some support functionality that you always need when you're making test benches, like checking values, checking that the value is inside a range, checking that the signal is stable, waiting for a signal to get stable, waiting for a change on a signal, and waiting for a value on a signal. And of course, you can report alert counters, and then you have bus functional model support and examples and so on. So I thought it would also be interesting to show this graph or diagram showing the history of UVM utility library. So basically, it all originated in something called Digitas utility library. Digitas was a company that existed a few years ago, making a utility library which looks quite a bit like the one we have in UVM utility library today. Then Digitas was acquired by a company called Data Response. And after leaving Data Response, we started Bitvis, and we wanted to have the same functionality again. So basically, we made utility library from scratch, but it's very similar to the Digitas utility library, now called Bitvis utility library, released in 2013. And I think Lars also told me that vUnit, the logging and check capability of vUnit, also inspired by the Digitas utility library. But Digitas utility library was a commercial library. It's actually sold at something like 7,000 euro or something. Good commercial product. Then in 2016, we in Bitvis, we decided that we will make everything open source, and we will make it also extended with more functionality. So we created what we called UVVM, Universal VHDL Verification Methodology. And then we included the Bitvis utility library in there. And the main change then basically was that we also said that from now on in UVM, we will only base things on VHDL 2008. So the Bitvis utility library is still available and is a VHDL 93 version. And as Jim also mentioned, the log alert package in OSVM was also inspired by the Bitvis utility library. So just want to mention ID-based verbosity control, because that's quite important. You all know what it means. Basically, it means you have different IDs that you use in your log messages, and you enable and disable different IDs to make your log messages visible or to block them. So for instance, you can have an ID called ID packet header, a general ID, can be used for any protocol. So for instance, if you have an Ethernet protocol, you would have maybe inside your analyzer, you would have a log message with ID packet header as an ID, and a message saying that packet header has been received or detected. And of course, you can define your own IDs in here as well. So then verbosity control will determine which messages will actually be shown. And we try to do that with pseudo quasi-oriented, object-oriented approach, where we use enable and disable methods for the different IDs. So basically, we can do enable log message on ID packet header, which means that the log message for ID packet header will be shown. Otherwise, it will not be shown. And this could be dynamically enabled or disabled from the test sequencer. And being enumerated or using enumerated types has, in my opinion, some good advantages. It's guaranteed the right operation at compile time. It's checking everything. And it's also a good way to reduce the number of unique IDs, because people tend to make IDs as they think they need them. And that means they're making hundreds, thousands of IDs because they think they need them. But it's creating chaos. So ID-based robustity control, I think it's really important. And also, if you want to make a priority-based robustity control system, you can always do that on top of an ID-based robustity control system, but you cannot do it the other way around. So let's show you some examples of some of the methods or procedures here. So the log method is quite central. The very simple version of it is just the log command, a message ID, and a message. And there's an optional scope that basically tells you from where did this message origin. Could be put anywhere in your design or test bench. So for instance, it could be in a test sequencer as a section header. Then you would use a special ID log header, or some other. I think there are 2 or 3 of those. And it will give you the transcript you see below with a sort of a header-like transcript. It could also be as a normal progress report in a test sequencer, like this one, checking registers in UART4. And then you get a simple transcript like the one below. Then you can also have these in support processes or support entities. So for instance, if I have a process that applies data into my filter, then I could trigger maybe that process from the central sequencer. And when it is triggered, it has a log message saying that started applying new packet. And in this case, the scope also makes sense, because now you can see that the scope shows that the message came from p packet apply process, not from the test sequencer. Or most commonly, it will be in procedures or functions, typically BFMs or whatever, where you basically log what you're doing. So for instance, if you're receiving some kind of packet-oriented protocol, you'll have a log message saying that you have detected the packet header, you have detected the address, you have detected the payload, you have got the correct CRC, and so on. And you will have a log message for each of these happenings in your analyzer. And that means you can have a good progress report in your transcript afterwards. And of course, the very good thing about the verbosity control using IDs is that you can control these on an ID base. That is, the good thing about that is your messages or log messages are or cannot really be prioritized properly, because basically you cannot give a log message a priority before you make your test bench or before you run a test bench, because the priority of your messages depend on what you're doing at the moment. So when I'm debugging my protocol, the first thing I want to see is the packet header, to see that I can actually detect it. And that means ID packet header is extremely important to me. That has the highest priority. But once I know that I can detect the packet header, I can see the source address, the destination address, I can see the payload, and I can even see that the CRC is okay, then all of that has low priority. Then it has a much higher priority that I get a log message saying I have received a packet and it was okay. So priority change during the run. And you can have control the verbosity using these IDs, and you can also use individual verbosity control at every level in your test bench. So basically, you have 2 axes. So log is quite important in this system. Oops, something happened here. Sorry about that. Another important function is the check value or procedure. It's a check value. And basically, it checks a value against an expected value, or it could also be a Boolean check. And the trigger will alert if it fails. You can also have a post acknowledge depending on your verbosity control settings. And of course, there are overloads for different types. The check values are either functions with a return value or procedures with no return value. So for instance, inside the test sequencer, you can have a check value checking that your bus system data out is zeros because it's an OR bus. If it is not, it is an error. And then you have the message saying what should happen here. The DOut must be default inactive. And the last IRQ_TB is the scope. That's optional. So if everything works fine, you get the blue transcript where you just get a message saying what happened. The check value was okay, and also get your message. If it fails, you get an error indication, a timestamp, a scope, and a mismatch report saying that the value was so-and-so, whereas you expected so-and-so. It's quite useful when you do debugging of your test bench. Then you have alerts and severities. Basically, an alert is the base version of the complete alert handling. So you have an alert with a severity, or you could write a severity directly, like a warning, error, or whatever. So for instance, error and then message and a scope. This will directly initiate an alert. This is normally not used standalone, but as a part of a checker. All the alert levels, severity levels, are counted separately, and you can set alert stop limit so that it stops, for instance, when you have reached 3 errors. You can also choose to ignore the alerts if you want to, if you need to. For instance, if you provoke errors in the system, and so on. Other checks in the system is to check value in range, check stability. I already mentioned that. And I just want to show this await procedure because it's quite good. Because very many test benches are actually just running and doing nothing because they're waiting for something to happen. And you get absolutely no idea, no indication that it is hanging. So you can do, for instance, a wait value on an interrupt signal, and you expect that interrupt to go to 1 within a given time window. So at the earliest, within after a given time, and at the latest before a given time. Otherwise, it will time out and give you an error. So that means that the simulation will actually tell you that something wrong happened here. Yeah, it's just like this. Await value, your signal that you're waiting for should go to 1 at the earliest after 0 nanoseconds, at latest after 2 clock periods. Otherwise, it's an error, and then you have your message. So I won't go through all the different procedures and functions in this library. You can have a look at the quick reference and see for yourself. It's extremely user-friendly. You will be up and running in 20 minutes. It's extremely low user threshold. You have advanced functionality when needed, but advanced functionality is basically hidden from starters so that you can actually start using this library and only see the simple use of this library. It's quite well documented, PowerPoints, a webinar, quick references, and so on. And basically all it takes to get started is, after you download the library, of course, is to compile it as instructed, a few compile commands, add a use clause for the library inside a test bench, and then apply any other commands you want to, like, for instance, log or a check value, and then you go. It's a quick reference for everything in our system in UVM. It's a quick reference for utility library. Looks like this. Give you an overview of all the different categories of procedures and functions. And if you look deeper down in the quick reference, you will get an overview of all the different overloads that exist in this case for the check value procedure. So you can see the overloads, you can see examples, and there's a description also on the right-hand side there. It's quite easy to get started. With the utility library, we also provide quite a lot of BFMs. In this case, it's showing the Axi4Lite BFM and showing the Axi-Lite check procedure. Basically, it's like any other BFM. It has just a high-level transaction where you write the address value, the expected data, the alert level, the message, what's actually happening, and a clock and the signals you need. And this we have also similar BFMs for Axi4 Stream, Avalon, and so on. Quite a few different interfaces. These are also all open source and free. So, but the main message in this presentation is not utility library. Utility library is, I think, very good for quite simple test benches, and it's also excellent as a base infrastructure for more complex test benches. But for more complex device in the test, you have these issues. You have more interfaces on these FPGAs, more simultaneous activity on the interfaces, and then you have value and cycle related corner cases. So a value related corner case could typically be that your protocol could have from 0 to 256 bytes as a payload. Then, of course, at least 0, 1, 255, 256 bytes are value-related corner cases, whereas a cycle-related corner case is, for instance, in a UART, when you receive data from the lower level in the UART, that is, you have just received the stop bit, and the data is passed on to the buffer or to the FIFO, and at the same time, you are reading the previous data from the CPU. And you're doing that at the same cycle, or one cycle apart, or 2 cycles apart. Those are cycle-related corner cases. And the reason these things often fail is that basically one if in your code is blocking another if or another else. And you will not, it's really difficult to detect because it will only happen in 1 out of 1,000, 10,000, or 100,000 cases, and you will definitely not hit that in your simulation, and most probably also not in the lab unless you actually aim to hit it. So to actually verify these more complex issues, you may need some kind of structured constrained random. You may need some kind of structured functional coverage, some kind of scoreboarding, and of course, it would be great to have reusable IP and libraries to save time and make this more using a more qualified system. So if you use things that are existing today, I'm showing the value-related corner cases as quite green, meaning this is something we handled quite well. And the reason for that is, if you look at, for instance, OSVVM, OSVVM has very, very good support for constrained random and functional coverage, which is excellent to detect value-related corner cases. But if you look at the interface, multiple interface related issues, cycle related corner case issues, that is not covered well at all with, I would say, existing systems or methodologies. So how can you handle that? Well, the only way to actually handle that properly is to have tight control over interfaces. And in order to have tight control of the interfaces, we need to have a very good architecture. So architecture is the key here. Let's go to a chip-level functional scenario, looking at an FPGA like that. And most designers or companies would do some kind of sequential testing here. They would write data into the process interface, and check data out of the UART-TX. Then write some data into the UART-RX, check data out of the process interface. Same with the Ethernet, both sides, and so on and so on. You find some bugs, it behaves fine. You may even have detected some validated corner cases, and everything looks fine until you start with parallel operation. So then you start putting data into UART at the same time as you read the previous data out of the process interface. And suddenly, your well-behaving UART is not that well-behaving any longer. It basically fails, it has a bug, and is cycle-related. Same problem you could have with the Ethernet and UART data being provided at the same time. And the interrupt controller suddenly couldn't handle the fact that it received 2 interrupts, 1 cycle apart, 2 cycles apart, or so on. And of course, the same then with the DMA and so on and so on. So that means you could have lots of these multi and cycle-related corner cases, which is not that good. And these bugs are really hard to find. You find these multi-interface challenges in lots of different scenarios. I just showed you a few of the sort of typical scenarios with lots of different interfaces and an FPGA. But you could even have it in a simple module like a UART, because in a UART, you basically have 3 channels that are operating individually or independently. You have the bus interface, you have the TX, and the RX, and they basically all operate individually, independently. So you have different types of corner cases in all of the systems. So corner case categories, I mentioned it, it's value-related, it's inter-value-related, it's cycle-related, and of course, you can have also things that are a combination of the two, which are really, really hard to detect. Of course, a corner case is not a problem by itself. It's only a problem when the design doesn't work for this case. I mean, any specification will have corner cases. Any design will have corner cases. Thing is that you need to make sure that there are no bugs related to these corner cases. The problem is then when these bugs are detected late in the FPGA development or not detected at all until delivered to the customer. So it's basically all about detection. What are the typical test bench approaches in different companies? How do designers handle these cycle-related corner cases? How do they handle multiple simultaneous active interfaces? First of all, there are quite a few who don't know that this is actually a problem. Then you have those who know this is a problem, but they couldn't care less. They don't want to spend time on it, and they just believe that, no, my design will probably work. Then you have those that know this is a major problem. We have to check it. We'll check it in the lab. And that could be a good idea, but most of the time it's not a good idea. You could normally detect more cycle-related corner cases in the lab, but the chance of actually detecting all cycle-related corner cases is close to 0 also in the lab, because you tend to do things in the same order, in the same sequence, also in the lab environment. Then you have those that know this is to check by verification. Start by adding threads on all the different interfaces. And of course, you have to do that because in order to verify multiple interfaces at the same time, you have to be able to control all of these interfaces at the same time, which means you need at least 1 thread per interface, or per channel, really. Then there are most people who do this, most designers who know they have to do this, make a structure which is totally ad hoc and very, very often totally chaotic. Not reusable at all and not understandable for anyone else. Then some companies have seen also have a fixed structure. So they actually do have a structure. They do have a way of handling this. And basically that means they have a system where they handle this by applying or controlling the interfaces via lots of different processes. They might not even have a test case sequencer, a central test case sequencer. Some have it, some don't. and some even put all these different processes in a collection of interface control processes. And this looks nice on the surface, but the problem is that it's very easy to lose the overview here, and especially in a way that those who design the system, those who know the deep details of the system, they can actually understand it, but the rest of the team usually cannot understand this, or it's really difficult to understand. It's difficult to reuse, and it's difficult to synchronize the different processes that have to handle different interfaces. So the good solution here would be to have a good architecture to handle this, of course, that's pretty obvious. Good overview and also good reuse and synchronization, which is what this next slides is going to be about. So let's look at a scenario here when you want to check data out of a UART, the UART TX. So we have a test sequencer using a bus functional model and this SBI, right? SBI is just a simple bus interface. It's a single cycle, very simple interface with a write, read, and a check procedure that can be issued from the test sequencer directly towards the UART register interface. And it could also have a UART transmit BFM and a UART receive or expect. But as I said previously, the test sequencer is a single thread, so you can only access one interface at a time. So you cannot detect these site-related issues. So that means we have to have multiple threads, as I just showed in the previous slide as well. So we have to have a separate process or thread to do the transmission onto RX and the reception from TX, and use the BFMs from these procedures to access the device in the test. But you also need some kind of communication between the processes. Of course, in simple cases, they could be totally independent, like for instance, if you just apply data to a filter. But for more complex scenarios, you need to control them and you need to communicate between the different processes that control different interfaces in your verification system. So how do we handle that? Well, we could trigger p-receive from the test sequencer and give it expected data. So the test sequencer basically tells the p-receive process that, hey, start receiving or expect data and expect these data. Then we need to control the severity if it receives the wrong data, unless that is fixed, of course. So we need to send that to p-receive as well. Unfortunately, p-receive sometimes doesn't detect this trigger pulse because it's busy receiving data from TX. So that means we should send some kind of acknowledge from p-receive to the sequencer. We can't wait forever for the acknowledge, so we need a timeout with error handling and reporting. So basically, you're adding more and more different issues, adding more and more signals, adding a more and more complex protocol to this system. So what do you do about this? Well, if you look at, we'll take one step back and look at the design system. We can see that the structure of an FPGA design, a module design, is given really proper attention. The design is split into standalone modules, like you see on the figure to the right there. The modules are all controlled from a sequencer, typically an external or internal CPU that controls the system via a bus system. This is a typical design structure, and most probably uses some kind of standard bus system or a simple bus system like the SPI. The test bench structure, on the other hand, is very seldom given sufficient attention. Going back again to the design structure, I mean, this yields a huge overhead. If you look at the code overhead that you have in your design, you have a huge overhead in your hierarchy, in splitting your design into modules, in making a bus system, bus interfaces, and everything. That's a huge overhead. So why don't we just make these by the communication, for instance, between the process interface and the UART by making a process to handle it. You can look at the process interface and look at the UART and handle everything and just add to that. Well, we know that that is a terrible approach and it will be total chaos. We know this from experience that we have to split our design into proper modules with a bus structure and bus interfaces. But on the test bench side, we seem to totally ignore the knowledge that we have on the design side, even though we have exactly the same challenges on the test bench side. So, of course, one obvious question here is, couldn't we just mirror the design structure? I'll come back to that. So, before we continue, I would say, when you look at test benches, I would say there are some wishful thinking here. We want to handle any number of interfaces in a structured manner, independent on whether that number is 1, 2, 10, or 50. We also want to reuse major test bench elements between module test benches. We want to reuse module test bench elements up to the FPGA test bench. It would be nice if you could read a test sequencer almost if it was some kind of simple pseudocode or easily readable software code. And to perhaps recognize verification specification in the way we write the test sequencer. And understand everything that's happening inside our test bench just from looking at one single test sequencer. That is, without having to look into lots of different parts of our verification system to understand what's happening. So let's try to solve this problem. So this is the situation we had in the previous case. And the problem specification here is that we have signals that need to be added between the test sequencer and the P transmit or P receive, removed or modified. We need a protocol, and this may be modified, may be extended. We have to have a knowledge of all the signals that go between the test sequencer and the P receive, and the protocol it uses. It's extremely cumbersome to write this over and over again, of course. So basically, these problems are the same problems we had before making BFMs. So rather than having all these issues that I show above, we make BFMs when we have these problems. So BFM basically handles this problem at the physical level. It's a valid minimum set of values and signals that go between the test sequencer and the device in the test. It's a hidden protocol. So basically you write PIF write or SBR write with an address and data. You don't care at all about the protocol or the signals that go between the test sequencer and device in the test. So the complexity is hidden for you. Of course, the readability is much better and it's very compact. Also allows painless modifications of signals, protocols, and features. We all know this. That's why we make BFMs. That's why I say it's exactly the same problem we have when you want to control P receive and P transmit. So we need a BFM-like solution. It has to be procedural or method, if you want to call it that. We have to have signals between the sequencer and the P receive. These are not physical signals as you would have towards the UART RX, TX, and the bus interface of the UART. But they are signals that you use to control the transactions between the test sequencer and P receive. So you could call them transaction level commands, but I think the expression transaction level commands is too broad because it's basically also covers BFMs and it's not properly defined. So basically we call them command distribution methods because they are methods to distribute commands from the test sequencer to these support processes. So in that case, we don't have all the signals seen from the test sequencer. We just use a CDM, command distribution method, which looks like the BFM. It's a receive UART X2A, telling P receive that, hey, you should now execute the receive BFM towards TX of the UART. Of course, we could make this slightly different so we can differentiate better between commands that are actually executed directly and commands that are distributed to other processes or components to be handled there. So in that case, we could just change the way we write the procedure and write receive and write the UART name and then the data. It will, of course, do exactly the same. And as I said, if you want to extend the functionality of that, we can just include more information like, if I don't receive 2A, issue a warning. If I don't get the data within 1 millisecond, issue a failure. So this all handles the problem on the sequencer side. We now have a BFM-like approach to handle this. But we haven't solved it on the executor side. That is p-receive and p-transmit. But before we look at that, let's look at what are now the remaining challenges. We have taken care of the readability seen from the test sequencer side. It's basically now just like a software sequencer controlling the design. And the protocols handle the procedures handle the protocols and information exchange between the test sequencer and this p-transmit, p-receive process. But there are still things we haven't solved, like, for instance, keeping the test bench overview for a device on the test with lots of different interfaces, efficient reuse at all levels, and some kind of synchronization mechanisms. So let's look at the executor side. Let's look at the receive side, p-receive. We have to detect the commands from the central test sequencer. It's pretty obvious. Then we have to execute the BFM, receive, command towards the device in the test. And unfortunately, a VHDL process cannot do both at the same time. So while the p-receive is handling the receive BFM, it can actually not detect a new trigger from the test sequencer. So for that, we need multiple processes. And if we have multiple processes, it's always good to combine them in an entity or a component. And so just call this component a verification component. So what are these verification components? What do they do? Well, they, of course, allow multiple threads because a component or entity can include multiple processes or subcomponents or hierarchy of such. It could have autonomous operation, just like a design module, a design component. It could be controlled via commands, also just like a design module. And you can encapsulate the complete verification functionality in the same way as you can encapsulate the complete UART functionality inside a module, which means it's more structured, better overview, and so on and so on. And you can have a standard interface toward this to control it. Of course, all these issues are exactly as for design. That means if we do it this way, we have solved the problem exactly as we do it on the design side. That brings us back to what I think is the best structure to mirror the design structure. So basically, the design modules in the design correspond to the verification components. And the module control status access corresponds to the sequencer talking to the verification components. That means we can write tests at a high abstraction level. We can divide and fix things and understand things in a much better way. We can avoid any complex parallelism, as we do for design. I mean, people tend to say that we can handle parallelism well on the hardware side. We cannot. It's pure nonsense. The only way we can handle parallelism in design is to do it in an extremely structured manner. Like, for instance, dividing parallel operations into different entities. Then we should split the test cases from the test structure. And we want the test sequencer to directly reflect the verification specification. So it should be easy to write and understand. So let's look at the absolutely simplest variant of a verification component. And obviously, that would be just an encapsulated BFM. So let's look at that. Let's look at a scenario where you have a test case sequencer that uses a BFM to access the bus interface. So it uses a BFM, the SBI write, simple bus interface write, with the address parameter and the data parameter. Now, the minimum verification component has to interpret the command from the sequencer in 0 time and then execute the right BFM towards the device in the test. So that's why we now insert the verification component between the test case sequencer and the device in the test. And the sequencer command to do this is almost the same as the BFM it used in the non-verification component solution. Looks exactly the same, but we have added one parameter, which is the first parameter, the SPI VVCT. That is the SPI verification component target. That basically just says that I want to do an SPI write with onto this address with this data, but I want to distribute this the execution of this SPI write onto the SPI VVC. So that will result in the above BFM being executed from the verification component towards the device in the test. And even now, with this extremely simple verification component, we have achieved something. Because if we have a verification component like this on the bus interface, on the RX interface, and the TX interface, then a test case sequencer can distribute a command to each of these verification components at the same time. Of course, there will be delta cycles in between the distribution of commands, but it will be in 0 time. So that means once it has distributed all the commands, all these BFMs inside the verification components can start executing towards the device in the test simultaneously. So we had added a mechanism to handle simultaneous execution on BFMs on different interfaces just with this extremely simple verification component. Now, when you want to make test benches and verification environments and implement it and understand it, I think there are 3 main areas that we really know should handle in a good manner. One is the complete test bench with the test harness. We have to understand the test harness to be able to understand what's happening. The second is the verification components. We have to understand what's happening inside the verification components to understand the system. And of course, the central test sequencer. We have to understand the central test sequencer to understand the actual test case and to be able to write different test cases. So if you look at the test bench and the test harness first, then UVM is really Lego-like. So when you build a test harness, you instantiate your device in the test, and you just connect your verification components onto the device in the test. So interface towards interface, just the same way as you would interface an IP in your design. Just connects the verification component UART TX to the device in the test UART RX, and that's it. Then you build a test bench with a test sequencer, instantiate a test harness. Then every single verification component has its own verification package. And that package provides a connection, provides a global signal between the verification components and the test sequencer. That means the test sequencer doesn't need to be connected to verification components other than through this global signal, which means you can change your test harness any way you like. And these verification packages, verification component packages, also provide all the methods that the test sequencer can use. So once the test sequencer uses or includes one of these packages, it has access to the verification components, and it has access to all the methods it can apply on that verification components. This also means that you can have verification component anywhere in your system, also inside your device in the test. In fact, you can also have verification components inside a Verilog device on a test because it's connected by global signals. So that means the test bench itself is easy to implement and easy to understand by basically anyone who understands hardware. So what about verification components? Let's look at the scenario here. The SPI, simple bus interface verification component. So what does it have? It has an interpreter receiving data. It has a command queue and an executor. The interpreter will look at the commands from the test sequencer and check, is this command for me? Is it for the SPI verification component? Is it for this instance? If so, is this command to be queued for later execution? If it is, I'll put it on a queue. If not, I'll just have a simple case construct on what to do. And that could be just casing on the operand of that command to see, for instance, was this command a flush queue command? Is it a terminate operation command, or is it a setup command, or whatever? Okay, so the executor will then see that there's something is on the queue. There's a command waiting on the queue. It will fetch that command from the queue. It will also, of course, case on what to do. In this case, for the SPI verification components, it will have three options. It could be a write command, it could be a read command, it could be a check command. And depending on which command it is, it will issue the relevant BFM. So the SPI write, SPI check, SPI read, and execute that transaction towards the device on the test. So it's that simple. And one very good thing about the verification components here is that you have the same main architecture in every single verification component. So that means you have a lot of reuse between verification components. Almost all the code will be the same from one verification component to another. The main differentiator will be the BFMs. But of course, you have to make these BFMs for all the interfaces you want to use anyway, independent of whether you're using verification components. You need BFMs. And that is the differentiating part here. And to illustrate that, for instance, when you have a UART BFM with the UART expect, transmit, and receive, and you want to go from that to a UART verification component, you can do that in less than 30 minutes. And that is, I think someone internally here could do this in 15 minutes. We have a script that generates the base template, and you just change a few parameters inside the system. Of course, when you have a verification component, I said it's easy to add more stuff. And you should add more stuff into the verification components if you need it. So if you, for instance, if you have something that is a verification component for a protocol interface, you can, for instance, add a bitrate checker, a frame rate checker, a gap checker, and so on inside your verification component. And they will just be standing there continuously monitoring whatever they're supposed to check. And let's now assume that you have a slightly more advanced interface, like, say, the Avalon pipeline interface, memory mapped interface. So that can issue a command, and it can issue actually multiple commands before it gets any response on the first command. That means we have to be able to issue command in one thread and check the response in another thread. In most test benches, that will lead to chaos. In this system, it will not, because all we do is basically take the command queue and executor and duplicate that. So the main executor will now apply the command part of the BFMs. So it will issue the command towards the Avalon interface. At the same time, it will pass on the command it received from the initial command queue to the next queue. So that the response executor now knows that, hey, a command has been executed. I will now be waiting for the response. So The second queue is exactly the same as the first queue, and the response executor is exactly the same as the main executor, apart from the fact that they now issue slightly different BFM commands. That means that you have a structure that is still very, very understandable and very structured. So now we've seen that the test bench and verification components are well structured. What about the test sequencer? This is probably the most important part of the test bench because this is where you spend the most number of hours. I would assume in a normally complex verification scenario, a complex FPGA, you will spend more than 90% of your time making test cases, writing test cases. So it must be easy to understand, to modify, and to maintain. So I'm going to show you now for an example of a verification plan step, what the code would look like in UVM. So if we look at the plain English first, what you want to do here is to apply data to UART RX on the device on the test, then wait for the RX interrupt to come out of the UART device on the test. And of course, when that occurs, we can read the RX data register. That's a good sequence to test out. If you would do this purely sequentially, using sequential BFMs only, then you would probably do it like this. You do a UART transmit. Of course, the UART transmit is in from the outside, so UART transmits in from the outside. We'll put data onto the UART RX of the device on the test. Then we will use a command that is available in the utility library, a wait value. I mentioned that previously. So we wait for RX empty, to go to 0. When RX empty goes to 0, that means it is no longer empty, i.e. there is data in the UART RX register. And this should happen at the earliest after 0 nanoseconds, at latest after 12-bit periods. Otherwise, it's an error. And after that, we know this data. We do an SPI check, reading the RX data register, checking that it is actually A1. So that's how we do it with a pure sequential approach. If we use verification components, what will it look like? Well, basically, it would look almost exactly the same. The only difference here is that we don't execute the BFMs directly from the sequencer. We tell the verification components to execute this. So first we tell the UART verification component, instance number 1, that it should transmit A1. Then we do the same as above. We wait for RX empty to go to 0. After that, we know that the data has entered RX register, and we do an SPI check on that register. So this is exactly the same as above, apart from the fact that it has been distributed to the verification components. There's one difference though, and I said that the SPI check is just a distributional command. So that means no time has now passed here since the SPI check was actually distributed. So I could do an await value, I could do a wait for 1,000 nanoseconds, whatever. Or I could do it in a way with synchronized things. We could basically wait for the SPI check to be finished. And we do that with an await completion command. And we send that await completion command to the SPI verification component. And this await completion command is slightly different than all the other distribution commands in the sense that the await completion command will not just pass on or distribute the command and continue. It will actually wait for this to come through. So this is a synchronization mechanism, and that means await completion will not finish until the verification component has actually finished executing that command. So with that, they are exactly the same. But whether or not you're going to use the await completion, that's basically up to what you're going to do after the SPI check. Now, the main advantage of this system is, of course, to apply data at the same time. So let's do that. Apply UART RX and read the previous data at the same time. So we do this with parallel operation using verification components. So we issue just a UART transmit and an SPI check at the same time. Of course, this SPI check will read the previous data. Whether that is A1 or not, that depends on the previous transmission. So in this case, we see that we can actually start the transmission at the same time. But I want to test for corner cases. So I want to read register RX data just after this has been loaded. That means I have received the stop bit, and some state machine decides that yes, I've seen the stop bit, I have received a good byte, and I will put it into the buffer of the FIFO. At the same time, I read the RX data from the CPU side. That's a corner case. So to do that, I use the UART transmit, and I do the SPI check. But before I do the SPI check, then I send another command to the same verification component before the SPI check command, and that is an insert delay command. And the insert delay command will do exactly as you would expect. It will insert a delay. That is, it will send the command to the executor of the SPI verification component and tell it to wait C frame time, that's a UART frame time, plus 2 clock periods before it is allowed to fetch the new instruction or new command. This is because I expect my corner case to be 2 clock periods after the UART frame time. But of course, I can never be sure of this. I'm just guessing now. So basically, I should be able to do this n times the clock period. And in order to do that, we just basically extend the range to include all possible cycle corner cases. So we have again the UART transmit, the insert delay, SPI check, and now we have an await completion. That is because we want to make sure that we are finished doing the complete sequence before we start on the next sequence in this loop. And now I have the number of clock periods before and after the UART frame time can now be any number from minus cycles before to a number of cycles after the time I expect the corner case to be. So I can just add enough margin and I will hit the corner case. Of course, I can make my own super procedure to handle this by basically just making a procedure doing exactly what I did above. Or even better, I can actually make the verification components themselves handle the sequences. So I can, for instance, do something like an SPI write to the SPI verification component, again specifying which address to write to, but rather than writing the actual data, I will tell it to generate random data and write this to buffer number 1 and repeat this for 256 bytes. And then I basically do the same thing on the UART expect side, where I just read from this buffer and expect the same 256 bytes. Of course, similarly for the other interfaces. Now I've talked about cycle-related corner cases because that's what I think is the most difficult part here. But people, of course, need to check for validated corner cases as well. So how should they handle that? Of course, they could do it with direct testing, no problem. But of course, constrained random is quite popular and quite useful, at least in very many cases. For that, you can use standard VHDL, you could use a utility library, or you could use OSEVM to generate values. And you can apply it in different ways, as I've shown you previously. The example here is basically the same thing as I showed you in the previous slide. When it comes to functional coverage, OSEVM is definitely the best system for functional coverage today. And we can control this from the test sequencer as shown below with the UART transmit command, telling the UART verification component that I now want to transmit random data. I want to generate this random data, put it into buffer number 1, put it onto the RX input of the device in the test, and continue to do this until I have reached a certain data coverage, which is predefined, of course, using OSVM inside verification components. So let's look at UVM here versus OSVM and then randomization and coverage packages. So basically, as we see it, we have the UVM utility library, we have the UVM verification component framework, we have the BFMs and verification components themselves, the actual IPs, verification IPs, and then you have OSVM with randomization and functional coverage. So in my opinion, these, as we see it here, is really complementary, and it gives us a unified VHDL verification methodology. I must mention, though, that we have been discussing this internally, and we're not sure if we're going to use this OSVM in the future, but at least that's what we're doing just now. Now, debugging. I said debugging is extremely important. It's 43% of, or at least what they say from this Wilson research, 43% of the verification effort is spent on debugging. And of course, debugging doesn't mean only debugging your design. I would assume most of the time you do actually debug your test bench environment. And UVM has built-in messaging to simplify this. So this is just showing an example of the transcript. I have left out some columns to make it easier to see on the screen. So the first thing you see is a timestamp. You see the scope from where this message origin, and you have the actual message. As I said, some columns are left out. In this case, you can see that at time 305 nanoseconds, from the UART verification component, instance number 1, TX, a UART transmit command was completed. That is, the BFM has actually completed. And you see the same for the SPI check below. So now we look at the BFMs as they have been executed. But you can also look at this from a different angle, like looking at when are the commands actually distributed from the test sequencer. Then we see that the UART transmit command was issued at time 2045 nanoseconds. And the dash greater than, or arrow, is just a way in front of the UART transmit. It's just a way for us to show that this is a way of showing that we're distributing this command. You can change the symbol for that in the adaptation package if you want to. But we use as a means to tell you that this is a distribution of a command. So at 20:45, that was issued. Then an await completion was issued at the same time. Then, since we're doing a await completion, we're waiting for something, and at 4005 nanoseconds, we did we issued an SPI check, and at the same time, we issued a await completion for that. So here we only see the distribution of commands from the test sequencer to the verification components. And of course, you can see them together to see the complete scenario. This is not the complete scenario, this is just showing two different things. So if I really want to debug my verification component or my verification system, I could look at this in more detail. So I could look at all the log messages that we provide, but for the UART transmit only. So it starts with the distribution of the command from the test bench sequencer. UART transmit. Then the interpreter inside the UART verification component will say that it has received the command. Then it will give, it will tell the sequencer that it has received it, and the test bench sequencer will receive the acknowledge on that. And when it receives that, the test bench sequencer can continue with its next instruction or command. Inside the verification component, though, the command is now fetched by the executor, which says that it will now execute this command. And of course, sometime later, it has been completed. The BFM has actually been executed. Then the executor is waiting for new command, and the interpreter is waiting for new command because no command has been issued. And if you look at this number 15, that's the command index. That's this command is given. So by looking at the command index, you can follow that specific command through the complete pipeline. But of course, I want to mention that again, the normal view would maybe just be to show when you execute the commands only. Okay, scoreboards. Scoreboards is basically something you do to check that the result is as expected, and a FIFO would be maybe the simplest solution for that. A more complex scoreboard could include out-of-order transactions, sending data from one source to one destination, one to many destinations, and so on. Could include modeling if the data is modified. In UVM, we have different levels of scoreboarding. So level 0 would be to basically have the sequencer controlling everything, word by word, telling the source what to send and what destination, what to expect. It could also be slightly more advanced by, for instance, predefining some kind of shared array or whatever, a buffer, whatever, and tell verification component A to fetch data from that, and verification B to fetch to compare against that or some other shared array that has the result. Those approaches are quite intuitive for people who are not used to advanced test benches, so it's quite good beginner's level. Then, as I said, you can also have the verification components themselves generating constrained random data and handling functional coverage. This is all handled excellent with the current system. And on the roadmap, we also want to introduce independent monitors and central scoreboard and modeling, but it's not been implemented yet. So what's on the roadmap? It's more functionality on the verification component side, like multicast, broadcast, more examples on constrained random and functional coverage, more support for error injection and monitors, and more advanced scoreboards, standard solutions for pipeline transactions and also out-of-order transactions. The system can handle that quite well. We don't have any standard solution for it, only examples on it yet. We have one internally, but that's not official yet. We also have a VVC roadmap. So you want to make an SBI, a full Avalon stream, and some other verification components. This will be determined by what we need internally and also on request. But what we hope for is that the VHDL community will start making verification components and sharing them. And I know that some companies or some people are actually doing that or making their own verification components today. So we're trying to convince them to share it. Okay, summary. The structure is pretty much Lego-like. It's extremely simple to connect. Reusable verification components, reusable verification component structure, which is equally important. Simple synchronization between the different interfaces. Clear sequence of events. And I think this is a logical evolution of your existing mindset. You have made, or people have made verification systems using VHDL. They know the language, but they don't have a good architecture, don't have a good solution. All I have to do is basically to use this architecture if they want to, and they can basically start using one verification component, one BFM, or even just one procedure from the utility library if they want to. So back to the wishful thinking. I think UVM can actually handle all of this in a very good way. And the only system that can do this with BFM's verification components and is openly available today is actually UVM. Some numbers on benefits. My experience is that judging from normal test benches, your saving potential on a 5,000-hour FPGA development project could be anything from 200-300 to 2,000-3,000 man-hours. And of course, also saving time for software developers. So how much you save, of course, depends a lot on what kind of type of design you have. If it's more data or sort of control, or if it's control or protocol oriented, you will save more. And it also depends, of course, on where you are today and how efficient, how structured you are today. Okay, I mentioned this as a framework, and people tend to be sort of afraid of frameworks. But basically, you can use utility library for all or any part of your test bench. You don't have to use the whole system. You can just use parts of it. You can have third-party BFMs or verification components wrapped to UVM if you want to. And you can use, as I said, any number of verification components or BFMs in your system. So if you have BFMs, verification components from third party or internally, you can just use, for instance, the Axial Light BFM or UI BFM together with that and combine it with any other approach you want. So you're not stuck or locked in a system. And of course, you can also combine with OSVM for any part of your test bench, whether you're using utility library alone or verification components. It gives you a very structured, well-structured methodology, and you can choose which parts you want to use. It is gaining momentum. I mean, UVM with the verification component framework was actually released this year in February. We got great feedback from users and on LinkedIn. It has been presented now on various conferences, and the interest has been great. So last presented it at DVCon in Europe, in Munich last week. Sorry, 1.5 weeks ago. Setting up courses across Europe. We had one in Stockholm in April, doing one in Munich in December, doing one in Holland, Netherlands in January. And we're also talking to other people about various courses. So how to get started with UVM? Well, detail in this. Basically, you can watch PPT's webinars, download from GitHub, see quick reference, run demo test bench. That basically applies for utility library and for the verification component framework. And of course, you can register for our verification course if you like. And feel free to connect on LinkedIn if you have any questions. Conclusions. In my opinion, VHDL is the best language for verification for almost all VHDL designers. I think we can all agree on that. Understanding, maintainability, and reuse are critical. That's what you should focus on. Test bench architecture is key for that. There's no standard, but it is actually really needed. UVM handles the critical issues, yields a very good architecture, significantly improves efficiency and quality, and allows the best reuse possible for VHDL verification today, due to a standardized interface with lots of examples, due to encapsulation, where you can reuse an increasing verification IP functionality. You can put lots of stuff into your verification IP or verification components. And due to the fact that there are already many available verification components and BFMs around, and hopefully more to come. And that's it. Okay, any questions?
Thank you for your presentation. Yeah, questions from the other attendees?
I don't think I have any questions. I've seen it before, and I've had a number of discussions with Espen as well. So
yeah,
I was familiar with what was presented.
Yeah, I guess Jim has also seen it before.
Yep.
And you saw it yesterday, Patrick.
Yeah.
Not all of it, but
it.
most of it. Yeah.
Yeah.
So it's Torsten.
Is Torsten there?
Yeah.
Any questions, Torsten?
At the moment, not. I have to look on the GitHub project to further dig in. I think I'm more the practical guy with examples and stuff like that.
Yeah.
I've some time ago I've looked at the GitHub project, but I hadn't enough time to dig into it deeper. So maybe next week or the next days I will look at it. But it sounds interesting, especially the synchronization or the sequencer side. At the moment, I do more unit tests, so I don't know if I need such a sequencer. But if there are more interfaces, I can understand that it will be tedious to write a lot of processes that act in parallel and to maintain this. So maybe a sequencer is a good idea, or it is a good idea, I think.
Yep. Right. So that means no questions. Well, that's very fast. That's good.
There are examples to integrate OSVVM randomization with UVVM on GitHub, I think.
I'm not quite sure if we have put the example for that on GitHub yet. But I mean, basically, it's. I mean, you can use OSVM just as you would do it in any test bench. You can just include it in a test sequencer or inside the verification components, as you would do with any test bench.
The sequencer itself is only another VHDL entity.
Yeah,
Okay.
or process. Yeah.
Okay.
So basically, it's straightforward to include OSVM there.
And all the connections between the sequencers and the sequencer and the VVCs is done by global signals. If I remember. Okay.
So that's handled automatically once you include the packages in your test bench.
So if I write a VVC by myself, I have to create such a package with global signals for all the interfaces. And prototypes for the procedures, and then I can use them in the test sequencer.
Yep, and there's a Python script to help you get started. So that can basically generate verification component template for you, and then you can use that, and it also tells you where to fill in your own code. Okay,
I have a look at it.
Yep, good.
And your philosophy still, though, is at the highest level, you have a single thread.
At the highest level, yeah.
Yeah. Okay. So you're doing single-threaded dispatch, and then you're doing independent threads down in the separate VVCs.
That's correct, yes.
So we could combine UVVM with VUnit. Sorry, so many U's and V's. And the sequencer could be controlled from a Python script from the outside world. Is this correct?
The last thing you said was?
Internally, the controlling and the controlling of the BFMs and the interfaces is done by UVVM.
Yep.
And the test run can be controlled by VUnit, testing several sequences.
Yes, it can be combined for regression testing. Yes, yes. Lars has done that.
Ah, okay. So this is a big picture.
Yep.
Yeah. And you know, Patrick, it'll work for things that work well with single-threaded dispatch. And the thing my concern is I have some examples of it here that aren't acceptable for release at this point, is that I do multi-threaded dispatch all the time, and have instead at the highest level have synchronization primitives that handle when the multiple processes need to communicate with each other.
But the system, I mean, I have discussed this with a few people who also asked for multi-threaded dispatch, and in most cases, when I discussed it with them, they found out that they could actually do this with a single-threaded dispatch and handle it because the verification components can do basically control everything. So
you could partition
they
it that
could be
way
almost autonomous.
if you're okay with fractionizing your test into multiple different pieces. So that means now your test, if you break it down into the separate sequencers, now each of those individual sequencers, you're going to have test 1, sequencer 1, test 1, sequencer 2, test 1, sequencer 3, or VVC1, VVC2, VVC3. And you're basically just now, with that methodology, splitting your given test across multiple different files.
Yeah, I mean, basically, you're free to do most things. I mean, you can have the central sequencer, but I only mentioned now just the simple case where, for instance,
no, I understand the benefits of having the lower level sequencers. I'm just saying some of the stuff I do that's not a very convenient way to do it, because it's going to, instead of allowing me to have a single multi-threaded dispatcher, now I have to split that file into multiple different chunks, where each one has a separate instance or architecture of that VVC, or the thread that's in that VVC.
Okay, so just to explain, I think you know the system, but the others might not know the system, so I'll just explain that. I mentioned that inside for instance, the UART verification component,
sure,
the executor would be able to do a transmit, a receive, and expect command. It could also do random stimuli and random checking. So that means you can add more commands to the executor, and you can also add sequences to the executor.
When you randomize inside the model itself?
Sorry?
When you randomize inside the model itself?
You can randomize, or you can make your own sequence locally inside your verification component.
How are you communicating that value to the other side that's going to be expecting that value now?
In that case, we're just telling that verification component to send data to a given buffer.
So it's sending data to a buffer, and then when it gets received on that other side, how do you check it?
You check against the buffer. If it's not modified. If it's modified, you need a model in between.
Okay. So you're effectively using a buffer as a scoreboard, and it's a single element, single value scoreboard, because what happens when you go through a FIFO or something of that nature where you have different burst rates?
At the moment, we have implemented a FIFO structure as an example, but the actual base element is a flexible queue structure. So we will very soon change that to also have out of order, if that was the question.
No, it was just that wasn't out of order, but out of order is a necessary thing.
All right.
Is my mic on? I think I lost my mic for a while.
We can hear you.
We can hear you now.
Okay, yeah, great. So I was just going to give a comment on the units tested with UVVM. I had actually not tested it together with UVVM. I tested it together with the utility library.
All right.
And make the integration. But from our side,
that's basically the same.
Yeah, UVVM is just a piece of code.
Yeah.
So as long as there are no overlaps in procedure calls and such, then there is no problem.
Yeah.
Then of course we have, which I presented last time, was it the time before that, our own COM package, which tries to solve the same thing, but which one you use, then they should be compatible, should be able to work together. I don't see any problems with that.
That's good.
I already sent an email to Espen about the structure of UVVM. I was working on a compile script for VHDL, so we can precompile the UVVM utility library with a simulator. And I think it would be better if the library is split into separate Git repositories. So you could include the OSVDM library as a submodule. I think this could be a big benefit.
Yeah,
But
we will.
there are
we will
modifications.
do that, to see if we can make changes that makes sense to us and to our current customers. But so I think what you said in your email makes sense. As also, I mean, Andre answered you on that email.
Yep.
Yeah. So I think you tried to explain how we use it and how our customers use it, and extremely important for us that the most inexperienced users have the lowest threshold. They should have an extreme low threshold. We want to make that should be the main target here. Simplicity for those who don't want to understand the details of VHDL or GitHub or whatever.
Yep.
So that's extremely important.
I think as long as OSVDM is as is and there are no modifications, if you have a submodule, then someone cloning UVVM all won't see that they're also getting OSVVM at the same time.
Yeah, you just have to supply
you're right. Submodule update. Yeah, right. There's another.
You don't need a submodule update. You just apply the recursive switch.
Oh yeah, you're right.
So
clone
recursive, and you get everything. And even if you do local updates like git pull, the submodules are updated as well.
Yeah, but so, we have to be aware that there are lots of users who don't even use Git.
Yeah,
so
I agree.
I mean, I mean, as you said as well, Patrick, a zip file would probably solve that.
Yep.
But I have a question to you, Jim. You still there? Jim?
Mute.
Muted.
You there?
Yeah.
Yeah, good. We discussed this issue about shared variables some time ago.
What's the issue?
The fact that you get a warning now with VHDL 2008 if you use an ordinary shared variable.
Well, that's not an ordinary shared variable. If you use a shared variable with an ordinary type, that's illegal.
Yeah,
but illegal.
I can't, as I said to you, I told you some time ago as well, I can't understand why that is illegal, because if you have one,
it's not part of my. It's part of going through the formal procedures of the participating in a working group and suggesting that change and getting somebody to work on it, and nobody's done that. So that's why.
Okay.
I don't have any arguments for or against it, and I don't. So. Yeah.
So you don't know the argument for it?
What's that? I don't really care either way, to be honest with you.
Yeah.
I have more pressing things that I have to work on from a standards perspective.
I can understand that. That's why we basically ignore the warnings.
I think
it's still I would be warned that is illegal VHDL code.
I think in VHDL you actually get an error, but there's
no. It's just a warning.
VHDL is a little more pedantic than others, isn't it? He's busted me on a number of things.
Yeah.
But in this case, it's just a warning, and I did the compilation for UVVM, and I get many of these warnings. I think what's going on in the simulators, they are detecting the old shared variables, and they are constructing getters and setters for the old variables. So it's like a auto declaration mechanism.
Okay.
So they are wrapping the old value in a self-constructed protected type.
Well, that's good. That means we don't have to do it ourselves.
we found some simulators which can't handle the old variables in VHDL-93. And I also found out they switched to VHDL 2008 in the newest version of their simulator, and they make the same mistakes.
Which simulator is that?
Vivado simulator.
Oh yeah.
So I have some code which tries to enforce an execution order. So if the variable is not set, it's going to the init procedure, and if it's always not set, go back to the init until the init is finished. So I can enforce the init as a first procedure, and it's not working. It's working in every other tool, but it's the same behavior like in VHDL-93. So I think they didn't really implement the feature of monitors for protected types.
Okay.
But why are you using the old style shared variables? Is there a special reason for that?
The reason for it is that it makes the coding much simpler, especially when you want to use shared variables as default inputs to procedures and functions.
Yeah, that's you can't pass a new shared variable to a function. Yeah, at the moment. Yeah.
So it makes it when we know that there's only going to be one writer, then and multiple readers, then we decided that was so much easier for us.
Okay. At the
So
moment,
we do use protected types for things that could be written to from multiple places.
Yeah, in my code I don't have any reason to use an old style shared variable, but I don't use functions then. I only use procedures, and well, then I have no problem with them.
Yeah.
Right. If you have global shared variables that are protected types and you want to use functions, you can just not put them through the interface and just use them in pure function.
So, yeah. But that's it's not good for maintainability if you want to use the function in another module. And the protected type shared variable has another name, then it don't work anymore.
It's for when you really have some global structure, like we typically have, I guess, for sure in the unit, but also I guess in UVM and OSUVM, that there are global structures internal to the framework.
Yeah,
will only exist in one instance.
maybe you can make an alias to a whole protected type. I don't know. Then you can make it portable and always use the same name in the function, in an impure function, and only in external you switch the name with an alias. I don't know if that works.
Yeah.
As long as it works, we just a warning. We just filter out the warnings in our compile scripts.
Does it work for VHDL or is it an error, Patrick?
It's just a warning.
Okay, I thought it was an error, but I didn't know.
I haven't tested the result. I just compiled it.
Okay.
But in the analysis phase, it's just a warning.
Okay.
Yep.
If it were an error, that were a showstopper because you had to compile all files with VHDL-93. So, but if it's only a warning, it maybe runs.
Yeah. Most probably.
Lars, can you switch to my screen, please?
I should be able to do that. There you go.
Can you see my screen?
Yeah, I can see
Or
it.
is this-
Yeah.
Yep.
Okay. I'm seeing the screen from Espen. Okay. However, so maybe it's a delay. So I hope I have everybody on the list. Yes. We just need to figure out how to move the recorded meeting to the other channel.
Yeah, you're right.
Or I will write an email, a hate email to YouTube. So yeah, I will open a new meeting mode, and on my list for maybe next meeting or the meeting after that is to get the presentation of FuseSock. So this is a packet manager for IP cores. I think this would be a nice project to see here too.
Have you spoken to Olaf?
Yes, he's a bit busy right now, but he is interested in presenting it.
Okay.
And yes, we have a long list of goals here for the project. I couldn't finish my summary on the goals here to see what's in common, what's the difference. So maybe we delay it to the next meeting because we had so much trouble to get YouTube to work. And what was the other working item? The license section. Yeah.
I just answered on your mail, but I can
Yeah.
put it in there as well.
Yeah. And maybe the question to Jim and Espen, maybe you can ask your clients and customers, what's the boundary to accept an open source project? Is it okay to name an open source project or a used library, or what's the boundary for a license?
What do you mean by boundary? Like what they I mean,
I think most projects or most companies won't accept a GPL license or
that's
LGPL
correct.
because it has a copyleft rule and other restrictive rules in it. So what's acceptable to as a set of rules which can be included in the license? Maybe naming the name of the author, naming the source of the library, like a URL to GitHub or whatever. So maybe you can ask how far they would go with a license, with an open source license.
At least I checked with some companies that work in the defense industry, and they are normally the more difficult customer. And they at least they said that the MIT license is okay.
Okay.
Yeah, I have the same information. I guess that the MPL or Mozilla public license I use, it's not totally permissive. So it has some copyleft, but it's still business friendly. But that also has passed internal quality reviews or rules they have at various military companies. So MPL would work as well.
Okay.
I think it's as long as you have a license which is one of the major ones, which is well known and all the legal issues has been thoroughly examined. I think they are okay with anything but GPL type of licenses.
Okay. So yeah, Lars, please paste your email text into this page here, and maybe we get some other comments. So
Espen,
this is
are you
everything
guys
on my list here.
Espen.
Yep.
Are you guys working on a replacement for stuff like functional coverage and such?
We are not working on it now. Nope, we are not. But it is something that has been discussed.
Uh-huh. Do you have limitations or identified issues?
No, I think the issue was more how this would work in the future.
You mean integration-wise?
Integration-wise, and with the overlap. So some worries around that. So, but so far, I mean, I don't know if you noticed, but half a year ago, I didn't mention OSVM in our presentations. And I think the first time I mentioned OSVM in our presentations was in Munich at the FPGA Congress.
Mm-hmm.
So basically, I thought it was good to mention it because I think it's a good combination. But it's an ongoing discussion that isn't quite terminated or quite concluded. It's the main reasons are future integration and the overlap that could be a problem.
Is the integration, the overlap, I guess it's around logging and such. But if we're talking integration with the actual random functionality, you have some random functionality today, right? Is those parts overlapping as well?
Oh, they're definitely partially overlapping, but that's no problem.
Okay.
No problem at all. We don't mind using the OSM randomization package. I even tell people that our randomization package or randomization functions are dead simple to use, but if you need anything that's slightly advanced, then use the OSVM version. So no problem, no problem there. It's, as I said, more the logging alert stuff, but that's a part of the discussion I guess we're going to have in the future sometime.
Yeah. We're not going to be able to avoid it.
Sorry?
Yeah, we're not going to be able to avoid it.
Able to
avoid it. We need to have that
no,
discussion
I don't think so.
sometime.
We have to discuss it at least.
But I guess as long as randomization functions does not include logging.
No, it doesn't.
Oh.
But the coverage does. So we have modified the coverage package a bit.
The randomization does too, because it does parameter checking.
Yeah, okay, so we probably modify that as well. But it's only minor modifications to have one common logging system. And the users have a switch they can set which decides whether they use our logging system as the modified code or the original code without, as in with two different logging systems.
And when you say you do ID-based logging, it's all based on enumerated type?
Yep.
And what happens when the user wants to have that be based on like their BFM names, like UART1 and CPU1 and that kind of stuff?
First of all, we definitely advise them to put that in different verification components or processes, because otherwise they can't do it in parallel. And if they do that, they just have a so-called ID panel, as we call it, separate ID panel in each process, in each thread. And that means they can be controlled independently. So you can have the BFM ID BFM switched on or enabled in one process and disabled in another process. And if the user is really old-fashioned and want to have everything in one single test sequencer, he can just change the name of that ID to be ID UART, ID BFM UART1 if he wants to. So it's flexible. But the recommended solution is to use just ID BFM and have different BFMs in different threads.
And are those accessible from the test bench level? Or are they accessible from the main sequencer? Are they accessible from other places so you can turn it on from anywhere?
They're accessible from the main sequencer.
Is that by global names or something, or?
Actually, I think that's the only thing that is available via a method and via a global variable, shared variable, configuration variable. So you can do it either way.
What's happening if we goes away and say we are integrating the logging mechanism into CoreLib? Could we combine all three logging mechanisms from VUnit, UVVM, and OSVVM into one?
No, you can't combine them.
Having hierarchy, IDs.
They are different approaches.
Yeah, OSVVM uses string-based IDs that are converted internally, uses basically a dictionary inside to convert those to numeric identifiers.
Okay.
So you can do a string-based lookup of the name, and then you return a number, and then thereafter access that number. You get the best of both, of having a string-based and having a fast lookup.
I think from my point of view, the string versus enumerated type kind of solution, that's something that can be agreed upon, I guess. So I wouldn't see it, from my point of view, I wouldn't see that as a problem, that we might have different solutions there right now. But the problem I see from VUnit's point of view is that the basic architecture of the logging and alert/checking is different. So that means that you can do different things in one system that you cannot do in the other. So it's not just a matter of changing the APIs to have different types, it's what you can do. And I think the major difference is that we completely separate logging from checking. We completely separate what we call channels. That is what the information goes out to display and what goes to files. Everything around verbosity control and such are separated. That's something that might not be as separated in UVVM or in OSVVM. So from my point of view, it's the architecture that gets reflected into the APIs that is the problem.
Okay.
So yeah,
we can have. We can probably, when we go into that kind of discussion, we could set up the examples and the use cases.
You're very far away now from the microphone.
Oh, sorry. Yeah, what I was saying is that we should probably set up what kind of use cases that we are trying to target and how we solve them. Then it's easier to compare different pros and cons, and whether or not, then it's also easier to discuss whether or not those differences can be overcome.
Yeah,
Okay.
I mean, what I meant by they're not possible to use together is that basically they are not. Whether we can actually reach an agreement or not on one common system, that is a totally different question. But as a user today, you have to choose one of the three. And from our perspective, the most important thing has been user friendliness and low user threshold.
Yeah, I agree on that. I don't think that when I look at the differences, it's not at the lower end. I mean, as you showed, you can say log hello world and it will come out as hello world.
Yeah.
So you can, if you do log hello world in the unit, it will be exactly the same. So the difference comes later on when you move beyond that very basic usage. So I think I agree with you. It's important that even though that you have the possibility to do advanced stuff, the simple stuff must still be simple. Well, there is no way for people to gradually take on new features of the framework.
Yeah, but I think this is something we need to we need to have more time to discuss, because we can't do it at the end of this meeting.
I mean, we have overlaps in the checking, in the logging. We have overlaps in what you presented today with how different threads, should we call them that, communicate. That's also something that we have different solutions for. So
Yeah,
there
likewise.
is overlap in various places, and as said before, that I think if we cannot achieve interoperability between the different systems, then there's no way that we can move to the next step and merge things. So, I mean, I have discussing with both you, Espen, and Jim, and at least now we can use both OSVVM and UVVM within the unit. That's kind of interoperability. So I was thinking about what you're talking about, Espen, about maybe doing a separate OSVVM type of package that's kind of moving in the other direction. But I mean, it's obviously up to you and what you need to do for your customers, but that would certainly be something moving in the other direction.
Yeah, as I said, I think we need to go through the if there are other systems as well we need to consider, and then spend some more time than we can actually do just now, because it's getting late.
Yeah, agree.
Okay, so are there any open items for today's meeting or questions?
I could add is I have asked the ADA guys at work, and regarding the string types and the dictionary implementation in ADA, in the ADA library, standard library, or the data types, and the first is our developers mostly use the unbounded strings from ADA, which seems to be a class with methods to work with the strings or manipulate the strings, but it's with dynamic memory allocation, I think. And the second is if you have the CNAT compiler installed, you can look at the source code of the container library, which is contains the abstract data type. So I have a quick look at it. I had a quick look at it, and they split the. For example, the dictionary type is split in two. There's a bounded implementation and an unbounded implementation, and both rely on a hash table implementation, which is in another package, and do some stuff around it to form the dictionary. So maybe some things we can use, but I don't think that we can use most or all of the things, because there are many constructs which don't are copyable in VHDL, I think. Yeah, but I will have a further look at it. Maybe we can get some hints to implement the abstract data types in VHDL. Yeah.
I just remember one question, Jim. You sent a white paper from Mr. Anderson also
Ashton.
about Ashna?
Peter Ashenden.
Okay, Ashna. Can I upload this on VHDL.net or is it private?
Didn't get any information on that yet.
Okay, so
Yeah,
let's
I would say put it up on our page for anybody within the group to look at. So if you could keep it private, that would be fine. You can share it with anybody in the group.
I think I can restrict the access to
Yeah.
uploaded files. Yeah.
That's fine.
Okay. So I think we can stop the recording.
Yeah, let's see what happens.